we can get a little more insight into resistivity and conductivity if we look a little bit more carefully at let's see what did this mean? Carriers, what did we call it? We said collide with the lattice. So we had this idea that they feel electric field, their velocity increases, they're accelerated, and then boom, they hit the lattice and they stop. And they go and hit the lattice, go, hit the lattice. So what's really happening? So let's imagine electrons in metal. That's our most common conductor that we study. And we know that metals are crystalline. So they have their atoms arranged in a periodic array like this. And they have these electrons that are free to wander around. That's what makes them a conductor. But what we haven't said yet is that the electrons travel as waves that move in between the atoms and don't hit them. Okay. A lot of high-level physicists and professors that see this are just completely appalled that I would say that, because this statement is not meant for them. This statement is meant for someone just learning physics. So if you do the quantum mechanics and the solid-state physics, you learn that electrons do travel as waves. And they travel with a wavelength that sort of depends on this periodic potential created by the atoms. And you can't really think of them as billiard balls. They're kind of like waves, and they're kind of like billiard balls. So it's not really that billiard balls are moving in between the atoms. Okay? But it is true that the waves move through this lattice, and they would never collide with it. In this ideal case, all metals would be superconductors. The tau would be infinity. The wave, the electron, would just go through here, happily move along at very specific wavelengths, and would never hit the lattice. Okay? That's the ideal scenario. But that's not really what's happening. We know that metals actually do have some resistance. It's kind of small. But what really happens is that electrons collide with a vibrating lattice. So the lattice is never ideal, because when you're at a finite temperature, everything that's at some finite temperature has some amount of thermal energy. So we know that these things are actually they're vibrating. And they're not all vibrating together. If they were all vibrating together, you could still think of it as a periodic potential. But they're vibrating in different directions and with different frequencies, with thermal noise, all this stuff. So the electrons aren't actually moving through a perfect lattice. They're moving through a slightly deformed lattice. And that is why the resistivity depends on, that's why you have some resistivity. And it's also why it depends on temperature. So if we were going to think about what is rho versus T, so here's temperature, and here's rho, the resistivity. If you want to plot it, the way it's usually given to you is actually based on the change from some point. So you start out and you say, I happen to actually know the value of rho at a certain temperature. So at some temperature T naught, I know the value of rho at rho naught, and then the way it's characterized is with the temperature coefficient of resistance. Which is called, the fancy name for something that we symbol is alpha. Okay? So all it really is telling you is alpha is kind of like the slope. The way the formula is usually written, or one way you could write it, is that rho at some temperature equals rho naught plus, and then you got to take that rho naught and multiply it by alpha and by T minus T naught. So it's just telling you for every change in degree of temperature and change in Kelvin, you multiply this alpha. It's usually really small. It's sort of 5 times 10 to the, I think, around minus 3. Depends on the material, of course. So it's not very big. You multiply that by the original rho, and that's how much of a change you get from somewhere else. So it's always sort of a linear thing like that. Now, this is just an approximation. It's not really linear over all temperatures, but over some small temperature range, if you know rho at some temperature range, it'll be approximately linear around that point. And this is the formula, and this is the thing that characterizes your material. And if we look at that, that would be in inverse kelvins. Right? Because it's just some factor you multiply by the temperature change in Kelvin to multiply the resistivity to give you the change in resistivity. So, but you can see why it depends on temperature, is because those collisions that stop the charge carrier are due to the atoms being in the wrong place due to thermal vibration. It'll also show you why we can use current to heat something up. If you pass a big current through something, then the electrons will move along, and when they hit an atom that's a little bit out of place due to thermal vibrations, they give it even more energy. Right? They dump their kinetic energy into the lattice. So again, that's two ways that electric current and temperature are connected.